Hello everyone, and welcome to AASC's webinar, Welded Connections, the Good, the Bad, and the Ugly, presented by Duane Miller. Today is December 3rd, 2015. My name is Christina Harbour. I am with AASC's Continuing Education Group, and I will be moderating today's presentation. I want to introduce today's speaker. Duane Miller is a recognized authority on the design of welded connections. He is currently the chair of AWS D1 Structural Welding Committee, a member of AWS D14 Committee, and a member of the AASC Specifications Committee. He has received numerous awards, including the AASC T.R. Higgins Lectureship Award and AASC Lifetime Achievement Award. He is a 3-time recipient of the AWS Silver Quill Award for excellence in his published work. Welcome, Duane, and I will hand things over to you.
Well, thank you, Christina, and good morning to everybody who's joining us on this webinar. I found that I rather like these webinars. It allows me to reach out, share information with you, and still stay at home. And for me, that's a treat. So thank you very much. I hope that the information that we have to share with you will help you all in your day-to-day tasks, whatever those responsibilities may be. We usually get a fair number of structural engineers, of course, who attend this seminar, or webinar. I hope that we have a number of detailers who have also been able to join us. And then for fabricators and erectors who work these designs into steel, I think we'll have information that will be important to you as well as to any inspectors who might have joined us. So thank you for your participation today. Our title is Welded Connections, the Good, the Bad, and the Ugly. I wish I could take credit for this title. Somebody else came up with it. I like the title. And the goal today is to share with you information that will help us all come up with better welded connections. Let's start by asking the question, what makes a welded connection good, bad, or ugly? To start, we'll go to Merriam-Webster's online dictionary and see the definition of the word good. And we see it's of high quality, of somewhat high but not excellent quality, correct or proper. And bad is defined as low in quality, not correct or proper, not pleasant, pleasing, or enjoyable. And finally, to ugly, unpleasant to look at, not pretty or attractive, unpleasant to hear, offensive, or disgusting. Now that we've defined these key words, let's go back to good. And I'd like to suggest that the words correct or proper are highly applicable to today's topic. I want to talk about welded connections that are correct or proper. And of course, that drives the question, what makes for a welded connection that is correct or proper? And I'd like to suggest to you that there are certain principles of connection design that should be followed. And when we follow those principles, we come up with good connections. Violate those principles, we come up with bad or ugly connections. Here's the outline of today's webinar. We're going to review 12 principles that make for good welded connections. And then, in the form of some case studies, in the form of examples, we'll look at good and bad welded connections. And then we're going to wrap up the day, the webinar, by looking at some ugly welded connections. Those are the case studies of actual projects where, some of these principles have been violated, and we ended up with something that's just flat out ugly. So there's where we're going, and let's start with the emphasis on the good and the bad. The first principle that I want to share with you, a correct and proper welded connection is strong enough to transfer all the applied loads through the connection. In other words, correct and proper means strong enough. Now, there's an immediate corollary to this principle. A good welded connection is not stronger than necessary. In my world, I find more welded connections that are stronger than they need to be as compared to weaker than they need to be. And so a good welded connection, of course it has to be strong enough, but it doesn't need to be stronger than necessary. Perhaps there's no greater contributor to overstrength welds than the weld symbol you're looking at on your screens. That weld symbol with CJP in the tail, CJP meaning complete joint penetration. And the official definition for a complete joint penetration groove weld is a groove weld in which weld metal extends through the joint thickness. Now that's the official definition. There are some unofficial definitions. These unofficial definitions tell us a little bit about the abuse. The first one I'd like to share is this: a weld specified JIC. What, you ask, does JIC mean? Just in case. A second example of where CJPs are specified: a weld specified when loads are unknown. Now that's a little disturbing. If the loads aren't known to size the weld, I wonder how the members were sized for these applications. Yes, a CJP generates the same strength as the attached material when loaded under static conditions. However, we really ought to know the loads when we're designing our connections. The third one, a weld specified for really important connections. We can make welded connections, even really important welded connections, with fillet welds of the proper size. We don't have to go to CJP. My fourth example, a weld specified when non-destructive testing is desired. There are non-destructive testing methods that can be applied to fillet welds, partial joint penetration groove welds. These tend to be surface evaluation techniques, dye penetrant magnetic particle inspection. For a volumetric inspection, we need to use something like ultrasonic inspection or radiographic testing. These inspection methodologies lend themselves to CJPs and has thus created a bit of a link between inspection and the weld type. But in fact, we can use other welds and even have them non-destructively tested. And the fifth and final example is a weld specified when no one wants to calculate the weld size. I fear this is commonly the situation. Instead of evaluating the required fillet weld size for an application, it's really easy for somebody to cop out and just say, use a CJP and go on to the next project. Well, the principle is that we need to make sure that our welds have enough strength to transfer all the applied load through the connection. And it doesn't need to be any stronger than that. Principle number 2, a correct and proper welded connection has a clear and direct load path. There's another way of stating that. Mr. Blodgett, my mentor, who incidentally turned 96 last month, said it this way: provide a path so a transverse force can enter that part of the member or section that lies parallel to the force. The late Bill Millick, who was Vice President of Engineering at AISC, used to say this: the force goes to the stiff part. The force goes to the stiff part. Well, let's make some pictures that illustrate what these two gentlemen have been telling us over the years. Here we have a beam, and we're going to attach a lug underneath the beam. Of course, we're going to weld it in place, and now we apply the load. Mr. Blodgett says the force goes into the member that lies parallel, or that we should provide a path for the force to enter into the member that lies parallel. The parallel member in this case is the web, and ultimately that vertical load is going to enter into the web. It goes directly through the welded connection, and the welded connection is uniformly loaded along its length. And here we have a good connection detail. Let's rotate that lug at 90 degrees. We won't change the lug, it's the same. We don't change the weld, we don't change the beam, we don't change the load. But our load path now is totally different. The force still wants to enter into the member that lies parallel. But do you see that the weld is no longer uniformly loaded along its length? we have a peak stress in the middle of the length of the weld. Now, to accommodate that, we can modify our connection configuration, and we can apply a pair of stiffeners. When the stiffeners are welded in place, do you see that we have a path now for the load to enter into the member that lies parallel? A very clear and direct load path. When we understand what we're doing, we recognize that we don't need to make the weld of the stiffener to the top flange. That's not part of our load path. We don't need to do that. As a matter of fact, we could cut that back and create a gap. The load along the length of the weld is still uniform because our load path into the member that lies parallel is still present. Let's rotate that beam 90 degrees. Now we have the web horizontal and the flanges vertical. Let's add in a lug that we want to use to transfer a vertical load. We weld that in place. There's the load. The load wants to go into the member that lies parallel. The force goes to the stiff part. In other words, this vertical load is trying to go into the flanges. Now, I hope that you can see that even though we have a substantial weld to the web, most of that load is going to be transferred into these two vertically oriented fillet welds because they're trying to go into the member that lies parallel. That's the primary load path as shown by the yellow arrows. We could leave that weld off and size the two vertical welds to carry the loads alone. If you want to weld to the web, that's fine, but we should look at the load path when we're sizing the welds involved. If we add a stiffener on the back side of that beam, now we are creating a path that engages all the welds and allows that load to be transferred into the member that lies parallel. Next, we're going to leave behind wide flange shapes and look at round members. And let's attach a lug underneath that round member, add in the fillet welds, and apply the load. In this case, the parallel members are the quadrant of the tube over here at 9 o'clock and over here at 3 o'clock. I hope you can see that we do not have a clear load path into the member that lies parallel. The weld is uniformly loaded along its length, but the problem is over here at 6 o'clock, where the load's being transferred into the tube. The limit state, or the deformed state of the tube, helps us understand what's going on. And I hope that you can see the straining that takes place at the weld toe, and the straining that takes place at the end of the length of the weld. That's the problem of this configuration. What if we rotate the lug 90 degrees? We put in those welds, apply the vertical load. The parallel portion is still at 9 o'clock and at 3 o'clock. Do you see that we still have a problem with this connection detail? The ends of the welds are going to be most severely stressed because they're trying to transfer that load over to that 9 o'clock, that 3 o'clock location. And the deformed state helps us understand what's being strained. Do you see the strains at the weld toes and the strains at the end of the lengths of those welds? That's the problem with this orientation as well. So now let's look at what we could do to remedy this situation. Here we have a bracket that extends all the way out to the 9 o'clock, the 3 o'clock location. And we have a good, predictable load path for this connection. Some of you will notice that or recognize that almost all the load is being transferred in the portions of the weld toward the end. If that's the case, we could leave off the weld between 5 o'clock and 7 o'clock because that's not very effective. Now, if you have to seal this up for architectural reasons or for painting or something like that, by all means, go ahead and do that. In terms of sizing the weld, designing the weld, we need to understand that that's not going to be loaded uniformly along its length, and the ends are the portions that are going to do the most amount of work in this case. Let's go to square tubes. And if we add a lug underneath the square tube, I hope all of you by now recognize we have a problem, because the parallel portions are the webs, if you will, of this tube. And so even though we might have a weld that's strong enough for the application, we don't have a good load path for the force to be transferred into the member that lies parallel. The weld is uniformly loaded along its length. This is not a strength problem in that regard, but once again we have a load transfer challenge here. The deformed state helps us see what's happening. I trust once again that you can see the straining at the toe and the straining at the end of the length of this weld. How can we remedy this situation? Well, let's try to fix it by rotating the lug 90 degrees. Well, we need to realize that those square tubes have the radius in the corner. Welders would prefer to weld to the flat and not get into that radius area. And even though maybe superficially we think we've solved the problem, we think we have a path into the member that lies parallel, we really don't have an efficient path. The ends of those welds are going to have the highest stress, and of course they're right in the location of the stress riser at the end of that weld. The deformed state helps us see what's happening at that location. And again, we have straining at the toes and straining at the ends of those welds. A better solution than just rotating the lug would be to also add an internal diaphragm. Now, I recognize that you can't do this in every configuration. The diaphragm has to be near the end of the tube so I can get it in place and weld it in place. But I hope you can see that now we've created a very effective load path for that vertical load to enter into the member that lies parallel. Another alternative, one that does not require welding inside the tube, would be to build a bracket up on the outside of the tube. Now the vertical load goes through the brown member, through the fillet welds, into the purple, and directly into the member that lies parallel. And we have a very effective load path. It's predictable, and we have evenly loaded welds along their length. Another concept that could be employed is to use a yoke type arrangement where the vertical load is transferred through the weld directly into the member that lies parallel. The weld's put exactly where it should be, and we have a very efficient transfer of load. I end up spending a lot of time in airports. This happens to be the Dallas-Fort Worth Airport, and I think this tent structure is there primarily to provide some shade for the summer for the people down below. But I look at the welded connections, and to this tubular connection you see a bracket. The bracket extends out to the 3 o'clock, 9 o'clock location on the perimeter so that the horizontal force is transferred into the member that lies parallel. A very elegant solution for this particular connection. So in review, principle number 2 tells us that a correct and proper welded connection has a clear and direct load path. Number 3, a correct and proper welded connection places welds in regions of low stress. A corollary to this principle is, when possible, pass major loads through steel, not through welds. Now that might seem strange to you for a welding guy to be saying, when possible, keep the loads in the steel, don't transfer them through the welds. But that's just practical sense, good engineering. Don't put your major loads through the welds if you don't have to. Now, to illustrate this idea, I have a cruciform configuration. You see on the gray steel, big arrows. That means big loads. And you notice that the gray steel is thicker than the purple steel. And the purple steel has a little arrow, meaning that the loads are smaller. I want everybody to see that these welds are all critical. All the load from the gray has to go through the weld, through the purple, through the weld, and out the other end. Notice that that same configuration could be redrawn with a continuous member for the gray, and now none of this load needs to transfer through the welds. The welds need to be large enough only to transfer this reduced load in the purple. So our weld size goes down, and the major loads are being transferred through the steel. That's the concept. Here's an application of the concept. I have a member subject to bending. Perhaps this is a bridge member. There's the continuous load applied to that bridge member, and that creates a moment diagram. Now, it's possible that somewhere along the length of that rolled beam, I have some areas where the stresses are too high. And in those areas of high moment, I might want to put on a cover plate that would allow me to reduce the stress in that region. But I want you to notice the end of that cover plate. And assuming I have a fatigue-sensitive application where I need to consider the fatigue categories and the stress range, I want you to see that this cover plate terminates in a high moment area. And that cover plate is designated either a category E or E prime detail. Now, the concept of putting the welds in areas of low stress simply means to make the cover plate a little bit longer. It still is a fatigue category E or E prime. That has not changed, but what has changed is it is now terminating in an area of lower moment. And it's a good illustration of this principle that, when possible, put welds in areas of low stress. Principle number 4 says a correct and proper welded connection does not introduce stress risers. Let me remind everybody that stress risers are only stress risers if there is a tensile stress component perpendicular to the stress riser. Now, there are a variety of stress risers that may be introduced by welded connections. Properly made welded connections may have stress risers. Here is an example. It's a T-joint. If it helps you, think about this as a bottom beam to column flange connection with a field weld. And what's designated here with the bright purple is a steel backing piece that is going to be left in place. To better understand this connection, let's take a figurative cut through the connection, and what I want you to see is the stress riser that's created in the root of the weld when we have a tensile load applied. Some of you may recognize this as similar to the so-called pre-Northridge moment connection detail that had some problems during the 1994 Northridge earthquake. And today, for high seismic applications, for the bottom beam flange connection, this backing is typically required to be removed. Now, the principle here is to avoid connection details where we create stress risers. The principle here is not avoid all use of steel backing. Look at this joint. It happens to be a butt joint. We have steel backing. When you look at the cross-section of that, loaded in tension, do you see that the stress riser is parallel to the applied load? In other words, this is no longer a stress riser. It's a planar discontinuity, but it's parallel to the stress. And the concept here is to make sure that we don't introduce stress concentrations. Here we have the same butt joint made with a PJP groove weld. I trust that you can see when you load that up in tension, we're going to strain the root. That's a condition we clearly want to avoid. Now, if it's the same joint but loaded in compression, particularly for static loading applications, we don't have a tensile load perpendicular to the stress concentration. This would be acceptable. The double-ended arrows are showing us we're now into cyclic loading. And for cyclic loading, this would be a condition we'd want to avoid, because the cyclic loads may cause fatigue cracks to initiate in the root of the weld. Next, we have the same joint, but I want to show it loaded in shear. If the area of the weld throat times the weld length times the capacity of the weld metal is adequate to resist the applied loads, there's nothing wrong with this configuration of pure shear loading on the application. There's a stress concentration in the root, but it's not perpendicular to the tension field. Here we have a fabrication detail that's going to create a stress concentration. And what I want you to see is a box section made up of 4 plates with CJP groove welds on the corner. In order to make these one-sided welds and using pre-qualified details, steel backing has been introduced inside the box. So far we're okay. The error has been made where 2 segments of backing have been butted together and not joined. This is going to create a stress concentration perpendicular to the stress field, assuming this box is loaded in bending. This is also a violation of D1.1 requirements. It violates AISC requirements for cyclically loaded structures. We want to avoid this kind of detail that is prohibited from all applications by D1.1 and for cyclic applications by AISC. What we want to have is continuous backing. If you have to splice long segments of backing, you can do so by putting in a CJP groove weld. I won't take the time to read these code words, but these are the code language that precludes discontinuous backing. Now, I've put in shadow the words that say except as permitted below, and there are some exceptions, but the arrow's pointing to the condition that is prohibited. As to the exceptions, AWS does have some specific exceptions where segments of backing transverse to the applied stress are permitted to be left in place for tubular connections. I'll leave you to examine those exceptions on your own. But this is the introduction of that segment, which incidentally was a new set of provisions added in 2010. The summary, principle number 4, a correct and proper welded connection does not introduce stress risers. Principle 5, a correct and proper welded connection is not constrained. A proper welded connection is not constrained. I think we've probably all learned a little bit too much in our materials courses at the university. You probably, like I, had a lab assignment or you observed a tensile coupon being tested in the testing configuration. And we pulled those specimens to destruction. We watched them locally neck and finally fracture. And from that, we plotted up a stress strain curve. And you'll recall that after the material yields, we observed what was called ductility. And it was the stretching of that bar, the reduction of the cross-section of that bar. And maybe you were even told steel is an inherently ductile material. Well, that's what we learned from these uniaxial tensile coupons in the university. And this phrase is an interesting phrase. Steel is an inherently ductile material. If you Google that term, you'll find a lot of people use that term. Here's a 2002 publication on earthquake protection, a screenshot from the book, and sure enough it says steel is an inherently ductile material and is thus very suitable for building and construction areas. And you know, in high seismic zones, we rely inherently on ductile behavior for energy absorption during severe earthquakes. Now, the authors also added in a footnote 16. And the footnote 16 says, although welded joints can be a source of weakness and have resulted in some failures in recent earthquakes. So we put it all together, and these authors are saying steel is very inherently ductile material, very suitable for building in earthquakes, but welded joints can be a source of weakness and have resulted in some failures in recent earthquakes. And another site that comes up when we Google that phrase. This is from a FEMA publication of 2006. There's the screenshot. Steel is an inherently ductile material that is capable of sustaining large deformations. However, the very efficient thin flanged sections make the conventional frame construction vulnerable to localized damage. So even though steel is inherently ductile material, there are apparently some negative consequences, and that's what this document tells us. And here's from 1999, U.S. Army Corps of Engineers. And they're talking about the inherent ductility of steel. There's the same phrase again. Structural steel is an inherently ductile material. The ductility of steel structures is achieved by designing connections to avoid tearing or fracture, and by ensuring an adequate load path to travel across the connection. This last comment sounds a whole lot like provide a path for the force to enter into the member that lies parallel. And despite this inherent ductile nature, apparently there is some designing that needs to be done to avoid tearing or fracture. Now here's a textbook by three friends of mine, and this is their 1998 edition. They've got a more recent edition, but this was the first edition, and I want you to note that this is not too many years after the 1994 Northridge earthquake. The title of the book, Ductile Design of Steel Structures. And these authors have it right. Let's read what they said. Many practicing engineers have wrongly believed for years that the ductile nature of the structural steel material directly translates into an inherently ductile structure. So they are saying this is a wrong belief, that the ductile nature of the steel doesn't directly translate into an inherently ductile structure. Let's continue on in the same text. However, there are many situations in which an explicit approach to the design of ductile steel structures is necessary, because the inherent material ductility alone is not sufficient to provide the desired ultimate performance. To achieve this ductile response, one must recognize and avoid conditions that may lead to brittle fractures, and adopt appropriate design strategies to allow for stable and reliable hysteretic energy dissipation mechanisms. Their words, not mine. This sort of thinking is relatively new in structural engineering. You see, the inherent ductility in the steel is what we see with uniaxially loaded specimens in the laboratory. But if we do things wrong in design, this same ductile material may not behave in a ductile manner. And we need to understand that because our welded connections need to be designed with this in mind. Now, it may be new in structural engineering, but this has been known for quite a while. Here's the textbook written by Barsom and Rolfe. Their book, third edition, came out in 1999. And here's what they say. Most structural materials exhibit considerable strain deformation before reaching the tensile or ultimate strength. However, under conditions of low temperature, rapid loading, and or high constraint, low temperature, rapid loading, high constraint, and then they define high constraint when the principal stresses sigma 1, sigma 2, sigma 3 are essentially equal. Under those conditions, even ductile materials may not exhibit any deformation before fracture. Now, how is this related to welding? The very act of welding creates residual stresses, and we need to recognize the influence of those residual stresses, and we may want to alter our connection design. And this is particularly important when our principal stresses, sigma 1, sigma 2, sigma 3, are essentially equal. Let's take a bar, make it out of 50 KSI steel. It has a given length. And what I want to do to this 50 KSI steel is apply a 50 kip load that creates 50 KSI if the bar is 1 by 1. And I want to calculate how much elongation I get. How much elastic elongation takes place. That's the delta L. And I could calculate that, and when I have a 10-inch long bar, 50 KSI steel, and I load it up to the yield point, it elongates 0.017 inch. And so for a 10-inch bar, it turns out to be 0.17%. Now let's take that same 50 KSI bar and heat it from room temperature up to the point of melting. We could calculate the delta in length due to thermal expansion. And when we do that, we find it expands 0.18 inch, or 1.8% for a 10-inch long bar. Now the importance is to compare these two numbers. Mechanically, we got 0.17% elongation. Thermally, we got 1.8% elongation. And here's what I want you to take away from this. The thermal expansion is approximately 10 times the yield point elongation. Now, why does that matter? Because the weld metal goes in hot and expanded. And of necessity, it volumetrically contracts. And it contracts, and to accommodate that contraction, something must yield. The steel yields and yields, the weld yields and yields, until finally the contraction strains in the weld metal are exactly resisted by the surrounding steel and the strength that it provides. That's why we have residual stresses in welded connections. And that's why we have to accommodate this ductility in the design of connections. Now let's leave what might be kind of theoretical and look at a real practical application. Here we have a piece of steel. We bring in a T, and we're going to kind of make this into a cross cruciform configuration. We tack weld everything together, and we start to deposit these welds. These welds volumetrically shrink. And as I continue to weld and weld and weld, I hope that you can see that I have a longitudinal shrinkage stress and another longitudinal shrinkage stress and a third longitudinal shrinkage stress that are all meeting together at a point. And I hope you can see sigma 1 equals sigma 2 equals sigma 3. And if you see that, then you recognize that at this point, the inherent ductility of steel is simply not going to be exhibited, and I'm more likely to get brittle fracture from this location. How can I mitigate that situation? Well, let's configure this and sequence the welding a little bit differently. First, I bring in the member and I do all the welding on that. It does all the shrinkage it's going to do. Bring in the other members and I've applied the snipe. Now the snipe is doing two things. It's clearing the weld that's in place, but more importantly, do you understand that when I start to weld this together, the snipe precludes the interaction of these residual stresses. And these elements are allowed to shrink by themselves, but these residual stresses no longer meet at one location. And that's the reason, for example, or one of the reasons why we have minimum-sized weld access holes, to interrupt the concentration of residual stresses when welds come in from different orthogonal directions. So a correct and proper welded connection is one that is not constrained. Let's go to number 6. A good welded connection does not subject the weld to bending. A good connection does not subject the weld to bending. This T-joint helps to illustrate this concept. As I pry it back and forth, as the red arrow indicates, I would expect to ultimately get a fracture probably at the weld toe, maybe at the weld root. because I've got the welding in bending, and this bending is causing rotation about the longitudinal axis of the weld. How can I fix this? Adding in a stiffener is going to be a great way to take care of that. Now the connection is no longer bending, and I have a much better system. Perhaps the overall configuration would allow you to rotate that gray member 90 degrees so this weld's basically in shear rather than being loaded in bending about the weld's longitudinal axis. A correct and proper welded connection does not subject the weld to bending. Well, we're through the halfway point. We've got through 6. Let's go to number 7. A correct and proper welded connection protects the toes and roots of the welds. Protects the toes and roots of the welds. I have some little sayings that I use to try to encourage good design. And for this concept, I say watch your toes and remember your roots. We're not talking about the 12. We're not talking about the 10 digits on your feet. We're not talking about your heritage. We're talking about weld toes and the roots of welds. And now a few examples of what we're concerned about. Here I have cyclic loading on a T-joint joined with some fillet welds. After enough cycles of loading, if I have a relatively large fillet weld, I would expect toe crack initiation. When my fillet welds are smaller in size, I would expect root crack initiation. I need to watch my toes and remember my roots. Now here's a single-sided PJP groove weld in a butt joint, and the concern here would be the root. This root is unprotected. We're going to be prying about the root of the weld, and this is not a good configuration. We can protect the root of the weld from this prying action by using double-sided PJP groove welds. It is still possible, of course, that with cyclic loading, I could get tearing from the root. From welds that are improperly sized, I could get tearing from the root. But this would be a much better configuration than the single-sided PJP where I would have tearing or rotation about the root. Watch your toes. Remember your roots. That's number 7. Number 8. A correct and proper welded connection has a clearly defined throat. A clearly defined throat. And my little saying, a nothing weld ain't worth nothing. Now that begs for a definition of what I mean by a nothing weld. And so here it is. A nothing weld is a weld that looks like what you wanted, but it ain't. Now somewhere, my first grade elementary school teacher, Mrs. Piat, is probably turning over in her grave, but my abuse of the English language might cause you to remember this idea. We want to watch out for these welds that look like what we're looking for, but they're not. So let me give you an example. Let's go back to our CJP groove weld. You want a joint that's fused through the full cross-section. That's your objective. But the contractor doing the work gives you this. Here we have welds that do not fuse through the full cross-section. Now this would not be a pre-qualified joint detail. That's why D1.1 would not allow this unless we did procedure qualification testing. But what I want you to see from this is visually, externally, these welds could look the same. But they're certainly nothing like what I want. The bottom example is a nothing weld. Let me give you another. Here we have a T-joint with tight fit. When you put on the fillet welds, you know what the throat is for this tightly fit T-joint. Over here we have the same T-joint, but now we have a gap in the root, an excessive gap in the root. And I hope you can see that the weld throat is nothing like what you wanted it to be. It looks like what you want, but it's a nothing weld because it's nothing like what you actually wanted. When we're designing welded connections, it's good to watch out for these situations where we might have nothing welds. We'd prefer welds to have a clearly defined throat dimension. And that takes us to principle number 9, which says recognize material properties. A correct and proper welded connection recognizes material properties. I like to put it this way: respect material properties. Respect material properties. Now, for this illustration, we're going to go to the work of Barsom and Corvink, who did a study as part of the SAC project. And some of you know that that was the FEMA-sponsored work that was done after the 1994 Northridge earthquake. And you can see that this paper was published in 1997. It was not research. It was actually a synthesis study summarizing the work of others. And in particular, they were looking at the through-thickness properties of structural steels. You know that rolled steel has some directionality associated with it. You might have been taught at school that steel is isotropic, but we actually know it's anisotropic. It is not the same in every direction. Now, it's pretty good. And compared to other materials, the properties may actually look isotropic. But in fact, we have some differences depending on the orientation of our test specimens. And that's what I'd like to share with you. The yellow arrow represents the direction of rolling. Generally, we get the best properties in the direction of rolling. Fortunately, we usually demand of our steel members the highest properties in the direction of rolling. That is, beams are rolled longitudinally and we load them in the longitudinal direction as an illustration. Now, we could call that direction of rolling the longitudinal direction. We could call it the X direction. Some people call it the L direction. Perpendicular to that, we have the transverse direction, the Y direction, the capital T direction. And in the through thickness direction, we have the Z direction or the TT direction. And what I want to do now, using Barsom's work, is summarize the differences in key properties in these different directions. To understand the comparison that I'm going to show you, let me take a moment to explain this chart. This is basically a histogram. The vertical axis is going to be the frequency of occurrence. The horizontal axis is going to compare two properties, the same property taken in different directions. If we had a perfectly isotropic material, we would have one bar that would represent 100% of the examples, and it would have 100% of the property in the two different directions. I trust that is clear, but the next examples where we look at the actual data will probably clarify any confusion. Now, the first thing I want to examine is the yield strength in the transverse direction as compared to longitudinal. The longitudinal direction will always be our reference plane because that's the data that's reported on the mill test reports. You get the longitudinal yield strength of steels when you buy them. And when we look at the data, we see that not all of it is the same in both directions, but the distribution is pretty well clustered around 100%. I'm not sure anybody would be particularly concerned about this variation in terms of the yield of the transverse to the longitudinal. Next, we look at the same property, yield, but in the through thickness direction compared to the longitudinal. And when we do that, we pick up a little more variation. Most of the data is closely clustered around 100%. But you see some data that's higher and some data that's lower. And that's yield. Next, we look at tensile. First, transverse to longitudinal. And we don't have a lot of variation in that case. Next, we'll look at the ultimate in terms of through thickness to longitudinal. And we pick up, again, more variation where it's skewed to the lower end on the left, as you can see. The next property I want to share with you is reduction in area. Just to refresh some of your memories, we get reduction in area from round tensile coupons. We start with the original diameter of the specimen. That allows me to calculate an original area. After testing of the specimen, we measure the necked region, and that gives us the final diameter, allowing us to calculate a final area. And then we calculate the reduction in area with the equation I'm showing. The higher the reduction in area, the more ductile the material. So using that measurement of reduction in area to represent ductility, the first thing to compare is transverse to longitudinal. And when I do that, I pick up more spread, and you can notice that in the transverse direction, I don't have as much ductility as I do in the longitudinal direction. Now, please remember, it's the longitudinal data that we get reports on when we purchase our steel. So in the transverse direction, we have some reduction in the reduction in area, reduction in the ductility. Next, I want to look at the reduction in area comparing the through thickness to the longitudinal. And when we plot that data up on our histogram, now we see something that is very flat, and we notice that there is a significant portion of the steel that has much less reduction in area, much less ductility as compared to the longitudinal properties of the steel. Now we need to remember that. And part of the reason we need to remember that is in welded connections, oftentimes I load the steel in the through thickness direction. And that reduction in through thickness ductility can lead to problems, specifically lamellar tearing. Now here are the summaries of these authors as it relates to through thickness properties, starting with the ultimate. And they say that we can plan on, their words, a conservative through thickness ultimate strength value can be derived from longitudinal values given by the relationship 80% of the longitudinal. And in the case of through thickness of the yield, they say 90% of the longitudinal. That kind of makes sense. Most of the data is to the right of this 80% bar that I'm showing on the graph. So they say a conservative estimate could be 80%. A conservative estimate on yield, they said 90%. Now to the through thickness issue. They have this statement. Generally, a minimum 20% reduction in area value has been used as a good measure of lamellar tearing resistance. However, lamellar tearing behavior of steel products is determined by a complex interaction of many factors related to material property, detailing, welding procedure, fabrication, and design. And so that's one of our design principles. We need to be aware of material properties. We need to respect material properties. And when we understand that, it starts changing the way we design welded connections. Principle number 10, a correct and proper welded connection is easy, economical, and safe to fabricate and erect. Now, all of my stories are illustrations only. They're not comprehensive. But what's easy and economical is usually what's going to be quality as well. And I want to start with a cover plate illustration. In this slide, you can see that the cover plate is wider than the beam underneath. That will require a transverse weld be placed, the beam be rotated, and then the longitudinal weld made. Even if the other sequences followed, it involves flipping of the steel in order to do that. That adds time. It adds on an issue that might be concerned. Look at how much simpler the job is for the fabricator if the cover plate is simply detailed to be more narrow than the rolled beam. A simple, easy to fabricate assembly that works just as well. So 10 reminds us to make sure that we do everything we can to make the job easy, economical, and safe to fabricate and erect. Number 11 encourages us to recognize commercial realities. A correct and proper welded connection recognizes commercial realities. The first commercial reality I'd like to talk about are the ASTM tolerances. And you know that our flanges may be tilted somewhat. One flange gets the dimension T1 and the other one gets the dimension T. And for shapes over 12 inches deep, T plus T prime has to be less than or equal to 5/16 of an inch. Sometimes those flanges go together, sometimes they go in opposite directions. And we need to recognize these tilt dimensions that might come in. It directly affects connection configurations. When we weld, we get angular distortion. AWS D1.1 gives us limits for those angular distortions. But the reality is we're allowed to have some angular distortion. We need to recognize these commercial realities. Let's go back to ASTM and start with tubing. ASTM allows for tubes to be out of round. The out of roundness is permitted to be 0.75% of the OD once we're over 2 inches. Now, 0.75% doesn't sound like much, but if I have a 20-inch diameter tube, that comes out to be 0.15 inch. Even that doesn't sound like a big dimension. But allow me to go to the structural welding code, and I see that when I abut the joints, I'm given a maximum allowable of how far off I can be. And that turns out to be 0.12 inch. Now what I hope you can see is that I've used up almost all my tolerance, I've used up more than my tolerance in my as received tolerance on the material. Now I cheated a little bit. Notice that I put the two pieces of tube in alignment. If I maintain the center line, then I split this tolerance, and I'm now within tolerance. The point that I'm trying to communicate here is that this is not a fabricator's issue, that they're sloppy. This is just the standard tolerances for our commercial materials that we normally receive. And so we need to recognize these commercial realities. Well, we finally made it up to 12, and we can start getting into some of our case studies. Our final one is that a correct and proper welded connection is aesthetically pleasing. Now, we need to remember that beauty is in the eye of the beholder, and different people might look at beauty a little different ways. And in some cases, particularly welded in steel construction, pretty doesn't matter. If we're going to cover it up with fireproofing and then put that behind wallboard and never is going to be seen again, aesthetics probably don't matter so much. But I'm seeing more and more use of architecturally exposed steel, and I always look at the connections. And I see some good connections. I see some ugly connections. So let's take a look at aesthetics for a moment. You probably heard the term form follows function. Actually, that is a misquotation of Louis Sullivan, who said form ever follows function. And this is the context in which he said it. He said this: it is the pervading law of all things organic and inorganic, of all things physical and metaphysical, of all things human and all things superhuman, of all true manifestations of the head, of the heart, of the soul, that the life is recognizable in its expression, that form ever follows function. This is the law. Well, that's what Mr. Sullivan said. Let's try to apply that to welded connections. I went to a hollow structural shape here, and I guess the ideal configuration would be no joint at all. Reality says we're probably going to have a joint someplace. And I'd like to suggest that directly welded, that connection is as close to ideal as you can get. And maybe you won't agree with that, but at least that's true in my mind. A directly welded connection is just about as pretty as you can get. Now let's contrast that with something I think is ugly. Weld a flange onto the end of the tube and put in bolts. Now, I'm not taking a shot at bolts here. You have to weld that flange to the tube, and so this is a welded connection. It's welded and bolted, but that just looks ugly. It looks like something that ought to be in a boiler room with pressurized steam inside, not a structural connection. And this is another one that I see. You cut a slit in the tube, put a plate through that, and then bring in the other plate, weld it up. I got to say, that just looks ugly as can be to me. And a directly welded connection, to me, looks much more beautiful and better fits the criteria of form every following function. Well, let's go a little step further. Look at connections in general. I think an aesthetically pleasing connection is a welded connection, not a bolted connection. Yes, it's my prejudice, but welds just look natural. I think bolts look, well, screwy. That's what I think. An aesthetically pleasing welded connection, in my mind, is directly welded. We're not going to go through gusset plates. We don't go through flange plates. Just welded together. That looks great. And I guess this is getting real deep into my opinion, but I think welded connections that are left in the as-welded condition look good. There's nothing wrong with ripples on a weld. There's nothing wrong with a little bit of concavity or convexity. When you hit it with a grinder, it seems to highlight it more than anything else. Grinding it seems to say we didn't make this weld right, and we had to grind it away. And I don't think that's aesthetically pleasing. So that's my opinion. You do with it what you'd like to do. I don't like them to be ground. Now this down in Miami, and there's this truss made of round tubular members. They highlight it, they illuminate it, that's the word I'm looking with different colored light. I guess it's through the glass, different colored glass. And I just think these are beautiful welded connections. And the welds are unground, and they're left in the as-welded condition, and everybody knows that was two pieces of members coming together. Looks great. This is Nashville Airport, and they have a beautiful network of trusses with directly welded connections. And they're beautiful welded connections. And I think they're very aesthetically pleasing, and they look very, very natural when you do that. I'm not the only one who looks at these kinds of things. There was a Modern Steel article earlier this year that talked about working with large trusses. And some quotations from that article. Large steel trusses are continually being pushed to span further, support larger loads, and to be more aesthetically appealing. The challenge is to develop efficient, cost-effective, and eye-catching designs through a collaborative effort between engineers, fabricators, and erectors. Continuing on, some of the more critical items to collaborate on when working on large trusses are splice locations and types. The preferred number of splices on any truss is generally going to be 0. But on these large trusses, it's usually not feasible. It is often the preference of steel fabricators to weld splices together in the shop, whereas erectors tend to prefer bolted splice connections. That may be. That doesn't mean field welding has to be avoided. But let's go on. However, when handling large trusses with large loads, it's often impractical, even impossible, to transfer the loads through bolted connections, so field welded connections must be used. Here is a field bolted connection of one of those tubular members, and it looked ugly, and so they wrapped a sleeve around it to make it look like it was a directly welded connection. Now, I'm not worried about these bolts. They had to do a lot of welding to make this bolted connection work. I'm just trying to illustrate the fact that bolted connections can really look ugly and welded connections can look very good. And it's not just me. There's a scan out of the article. We blow it up, and let's see what it says. It's talking about that connection. The latter was initially specified as site welded, but the hidden, ugly bolted connection, which was covered up with the sleeve and field finished, sped up construction and met aesthetic requirements. So there you have it. Bolted connections are ugly. That's what the authors said. Well, folks, we got through all 12 now, and I need not read you this summary, but I hope this is a summary that you'll use on your projects in the future. The design objective on my part was to make a list of things that were so generic it would be applicable to everything that you're doing. Incorporating these principles will help you come up with good welded connections and avoid the bad. Now, some of you have been waiting for this minute where we're going to talk about the ugly. And the ugly are some case studies of things that have happened. Remember our definition of ugly: offensive or disgusting. Let's see if these connections fit into that category. I'm going to use a little summary statement here. We'll have three categories of ugly connections. Some are pretty simple. I have one that's very serious, and then we'll finish with a couple that are just kind of silly. And so I want to learn from these. I want you to learn from these, and let's get started with that. Starting with the simple. This comes from my friends at Owens Steel. They were asked to take a wide flange section and build a box around it. No doubt there's an architect involved who wanted the column to look like a box. And so this is what had been specified as the desired configuration. My recollection is the walls of the box then were going to be 1/2 inch thick material welded to a very heavy wide flange shape. Now remember, the total of T and T prime could be 5/16 of an inch. And when you're going to box in one of these wide flange shapes, when you add to it distortion from welding, you're going to get a square that's no longer a square. And as you add sections together on this architecturally sensitive application, you're going to get members that don't line up. Owens was smart enough to make some mock-ups. And they showed with their mock-ups that the standard acceptable tolerances on the wide flange shape, as well as the distortion that was going to be created by these welds, was going to result in members that didn't line up. Having identified the problem, they then proposed a solution. And the solution was to make this box section like a box. And with that form of construction, they could maintain the square nature of the box and maintain it to a tighter tolerance that met the architectural requirements and made it into a practical application. I think what they did is remembered commercial realities. The second example involves a W13/90 that has a web that's 1/2 inch thick and a flange that's 5/16 thick. This assembly received a 1 inch thick doubler on one side and a series of stiffeners on the other side. A gusset plate that was 1.5 inches was welded in place. Now that's the configuration, and when you just put in some symbolic welds, you start to realize there's a lot of concentrated welding right in this location. Welds must shrink, and shrinking welds will create distortion. And when this was fabricated, they had excessive distortion. And you can see the porta-power jack being used to straighten some of these flanges out. You can see on the left-hand side the amount of deflection that's taking place on the wide flange shape. The angular distortion is noticeable, and all of this could have been avoided if a heavier column section or beam section had been selected. A heavier section could probably have eliminated both the doublers and the stiffeners. So this one became an ugly example simply because the commercial realities of welding and distortion were not considered. This is a brace element that's exposed as part of the architecture of a building. It involves a 5-inch solid rod. That rod is welded to a 3.5 inch thick plate. through the circular holes that are 6 inches in diameter are inserted some pins that go through a gusset plate to hold this in place. The weld detail that's called for between the rod and the plate is a CJP groove weld with 1/4-inch fillet welds. Now, this turned out to be an ugly example. For some reason, the welding was done in the field. There's the joint before welding, and there's the joint after welding. And I can hear some of you chuckling, even though this is a webinar. And I do hope that somebody removed this weld tab later on. And I hope they got out the grinder and ground off some of these dingleberries that are over here. And certainly this deserves a little bit of grinding. And the workmanship is somewhat questionable. And that was given to me by a friend who said, this is an ugly example. And I have to agree. But it actually gets uglier as we go further. Now there it is in the actual application with the pin installed, and there's the large truss that went into this building. But I want to look at this drawing a little bit further, and in particular I want you to look at the loads listed down below. The loads were supplied 24.5 kips of tension on either end. 24.5 kips. If we divide that by the area of the rod, we find there are only 1.25 KSI on the rod. When we take that same 24.5 kips and distribute it along the CJP groove welds, we find the loads on the welds are 0.23 KSI. Isn't that interesting? How did that happen? Maybe somebody didn't want to determine the weld size for the application and specified CJP. Well, let's go one step further. What if they had used minimum-sized fillet welds? That would be a 5/16, and for the applied loads on a minimum-sized fillet weld, of the lengths that were involved, it comes out to be 1.84 KSI, clearly adequate to use a minimum-sized fillet weld. In fact, if we calculate the capacity of the minimum-sized fillet weld, it's 278 kips, or 11 times the design values. Well, I couldn't stop at that point in time. No, I had to go one step further, and I had to look at the economics. The CJP groove weld required 26 pounds of weld metal. A minimum-sized fillet weld, which was still more than we needed, required but 0.023 pounds of weld metal, and we would have had a 96% reduction in the amount of welding. It would have been strong enough, it would have looked fine, and it would have required a lot less welding. I think that's an ugly example, and it goes far beyond just the appearance of the welds when we're done. Well, somebody cleaned it up, put it in a structure. It looks very elegant, but I think there's more to the structure and more to the story than what you see in this picture. I told you I go through airports, and so I snap photographs of ugly connections. There's a knife plate and another knife plate in order to make those connections. This is in my town of Cleveland. I'm supposed to be looking at all the plants in this botanical garden, and I'm looking at the connections that look better suited for a power plant than a atrium of a greenhouse. And so I'm not going to look at plants anymore. I'm looking at the connections. Not only do I have the flange connection, but I've got the knife connection over here. And it could have been made much more elegant, lighter weight appearing with directly welded connections. I'm sure it was done for ease of field assembly, but I just think it looks ugly. I went to Auckland, New Zealand. I get off the airplane. I see nice tubular steel with ugly connections. And this is the one that we were looking at before that got covered with a sleeve. Would have been a great example to cover it with a sleeve. That just looks wrong. Inside the building, I see beautiful connections that are directly loaded. I see the field erection connections that I think are far less attractive than the directly welded connections. Well, those are some simple examples. Now I want to give you one that is serious. We're told that those who cannot remember the past are condemned to repeat it. And your computer didn't just die. I'm trying to catch your attention for just a moment. I'm sure well-intended people designed and worked through this project I'm about to share with you. My goal is not to criticize anybody. My goal, rather, is that we learn from the experiences of others. And I want to tell you the story of the El Paso Performing Arts Center that was constructed in 1972. And of course, that was 43 years ago. Many of you weren't even born at that time, but you need to know the history of El Paso. Well, El Paso, during construction, here's a shot of it, some problems occurred. These are construction problems, not serviceability problems. Highlighted here in yellow is a compression ring that was part of the structure. The compression ring is 138 feet in diameter, and it is compression. A cable-type support for the roof went in here and put compressional loading on that ring. The ring was made out of 4 plates to make a box. The height was 2 foot. The depth was 4.6 foot. Because the loading was compression, the strong axis is oriented in the right location because of the tension loads that are applied to that box. The box was made out of plate that was 2 to 2.5 to 3 inches thick. Segments of these boxes were made, and then to make those chords into a circle, plates were welded to the end of that member. The plates were 1 inch thick. They required a CJP groove weld between the 1 inch plate and the members in the box. And then other segments were brought in, and that allowed for the creation of the circular configuration of this section. In cross-section of the joint, you see the 1 inch plate, the 3 inch plates on the outside that receive the CJP groove weld. And I think some of you will immediately see the problem. And what happened with El Paso is they got into lamellar tearing that took place in the brown member. And that was one of the first times that we had a lot of publicity about something that you and I know of called lamellar tearing. And this lamellar tearing is related to the through thickness properties of the steel. Here we see El Paso, but after portions have been cut away in order to facilitate the repairs. And the repairs consisted of gouging out the torn material and then restoring it with good weld metal. I want you to see that the final configuration directly ties the 2 3-inch thick members together. And the 1 inch thick member is attached through the root of the weld. Here we see a photograph of the repaired area, and you can see that the end of the weld has probably been ground or cut off here, but that's where the repair has been made, and now the thick is directly welded to the thick without having the 1 inch member intersecting through the joint. And that reminds us that we should remember or recognize material properties. We also had this issue of constraint, and I think you understand with these large welds we had a lot of constraint. We need to have welds large enough to transfer the load through the connection, but not larger than it needs to be. The El Paso experience prompted AISC to write an article in the Engineering Journal published in 1973, and you can still see that, titled Commentary on Highly Restrained Welded Connections. And in there is a figure, and it's identified as figure A. And even though the report doesn't say that this is El Paso, in fact, that is the El Paso joint that I just showed you. And the parallel lines are showing that there is directionality to the steel. And when you weld perpendicular, the weld axis, the attachment is perpendicular to the through thickness, we could get lamellar tearing. So that's a scan out of the Engineering Journal article. Now you'll notice that joint looks very much like the pre-qualified joint detail from AWS. And in fact, it's just like the one here shown on the right. Oh, this is one-sided. El Paso was two-sided, but it's the same basic configuration. There's no prohibition that says you can't put it over there. There's no prohibition on the thicknesses of these steels. And so these are pre-qualified joint details just like were used in El Paso. A 3/8" root opening, 30-degree included angle. That's pre-qualified. But it's not applicable or not appropriate for this joint detail. After El Paso, D1.1 added in these notes. Under the engineer's responsibility, it concludes with the statement that the engineer shall determine the suitability of all joint details to be used in a welded structure. It's not enough to just use pre-qualified joint details. As a matter of fact, there's discussion about that issue. And it says under the topic pre-qualified joint details, it says these details have repeatedly generated their adequacy in providing the conditions and clearances necessary for depositing and fusing sound metal to the base material. But it hastens to say the use of these details shall not be interpreted as implying consideration of the effects of the welding process on base metal beyond the fusion boundary, nor the suitability of the joint detail for a given application. Lamellar tearing is beyond the boundary of the weld metal to the base metal. And so this is a hint that's saying we need to be careful about these kinds of things. Now we're trying to remember and learn from history. And that's why I'm repeating this story. But if we don't repeat history right, there are no lessons to be recalled. Now this is a sketch that you can find on the internet. And this is talking about the El Paso story. But I want you to look at the sketch, and I hope you can see the differences. This is not a faithful reproduction of what happened in El Paso. Notice it shows fillet welds, not groove welds. Notice it shows fillet welds on the outside and not welding through the thick material. The geometry suggests the 1-inch plate is the same as the outside plates, even though it does say that they're 2.5 to 3 inches, but graphically you don't get that kind of image. And look at this. It shows lamellar tears, but the lamellar tears are shown in the 2.5-inch thick material, not in the 1-inch material. You see, this repeating of history is flawed, and we aren't going to learn the right lessons. Not if we don't accurately record history. Now, they do seem to have gotten the repairs right, because that looks very much like what I showed you from the photograph. I'm not going to take the time to read this. This is out of the AISC article in 1973. And I have reproduced the key elements that come out of the summary of that article. And so if you just want to use the handout materials, you'll get the key issues from that paper, or you can look up the paper yourself and learn from those details. Let's learn from history and not repeat it. That's the El Paso story. Well, I'm almost done because I have a few silly examples here, folks. And I had to cut out a lot of them that I had, but sometimes we just have ugly welds. And I have a few examples of welds that are just flat out ugly. Look at that. Didn't get made right, melted through, and somebody shipped it and put it in place. And certainly those are things we're trying to avoid. A lot of my friends helped me by supplying examples of some of these good and bad, ugly examples. I want to thank all of them for their contributions. And that wraps up my presentation today. I think it's now time to open for any questions that might have come up. Is that the right schedule now?
Yes, Dwayne, we're about on schedule, and we have time to answer some questions that have come in. As a reminder, if you have not yet entered your question into the chat, you may do so still. The first question that we have is regarding cost. Which is generally cheaper for fillet welds, fewer shorter welds of a larger size, or more longer welds of a smaller size?
That's a great question. I'm glad that somebody asked it. The answer is you make welds long and small for economy. The reason that's true is that when you double the length of the weld, you double the strength. When you double the leg size, you double the strength, but you quadruple the amount of weld metal. So our objective is to make welds as long as we can and of the smallest size. I quickly add the caveat on size. We never want the size to be smaller than the minimum pre-qualified size that we have listed in AISC Chapter J, and I think it might be Table 2.1. But we don't want to be smaller than the minimum size. Otherwise, we make it long and small for economy.
Okay, great. Thank you. And referring to this slide, slide 52, we have a question regarding this beam that is uniformly loaded. The question is, aren't the dominant loads in the weld the transverse shear in the section, and since the load is near the outer fiber, are those stresses very low?
Okay, that's a great question too. And yes, the loads in the weld are primarily shear, and I'm going to try to use my cursor here. Once we add in the cover plate, the stresses in this area get to be very low, but the challenge here is where it terminates. And I'm assuming fatigue, so we have fatigue categories to be concerned with. Check it out. Category E is not the stress in the weld, it's the stress in the base metal. And the base metal stresses at the end of that cover plate have not changed. The stresses back in the area where we have the cover plate, those have gone down. But the stresses in the beam at the end of that have not changed. And it's at that point that we have the category E or E prime detail. The concept of extending the cover plate is to get it into an area where the stresses in the beam are lower. So it's a welded connection issue, but not a weld issue itself. The weld metal would always be category F. Category F, D dot control. We can make the weld of the right size, but in terms of the welded connection, we need to pay attention to this termination. And the category E termination in a lower stress range would be desirable.
Okay, great. Thank you, Dwayne. The next question is regarding the nothing weld. What is the best practice, i.e., what does the weld call-out look like to prevent these? My understanding is that pre-qualified welds within D1.1 set limits to the fit-up between sections.
Well, that too is a good question. I'll try to get a little bit of artwork maybe to support my answer. But you probably hit on the right idea. Following the D1.1 code is a good way to avoid nothing welds. So, for example, and I'd sure like to find that quickly.
I think maybe 114.
Oh, thank you very much, Christina. I'll take all the help I can get. 114. Yeah, great, good. So in the top slide, we would have a weld that's made with a pre-qualified detail. The bottom weld, that would not be a pre-qualified detail for thick steel. Now, it is possible to qualify the welding procedure by test. We're going outside the code when we do that. Sticking with pre-qualified details helps avoid that example of the nothing weld. The questioner had it right. D1.1 has limits on the amount of gap. We're allowed 1/16 of an inch of gap without correction. When we exceed that, we need to increase the weld leg by the amount of the gap, and that compensates for that. Now, of course, to implement that solution, we need to be measuring the fit up before the welds are deposited. And so I think the principle here is we need to be cognizant that things can go wrong and take appropriate actions to make sure that we're using appropriate techniques to make sure to overcome those issues.
Okay, great. Thank you. The next question. AISC Section J5 allows for a 50% increase in fillet weld strength when load transverse to weld orientation. This seems to contradict the watch your roots statement. Why is this configuration stronger?
All right. Well, I will give you a quick answer. The why is it strong answer is really a long answer. I think the issue here is concern about whether we're violating that somehow. Let me try to be brief. In all cases, we need to remember our roots. We wouldn't want to have a single-sided fillet weld loaded transversely, even if that's given a 50% increase. We would have straining about the root of the weld. Now, the real issue is whether we have longitudinally loaded fillets or transversely loaded fillets, we have localized shear on the throat of the weld. And so we want to protect the roots so we don't have prying about the roots. Once we protect the roots, then we have shear. Now, as to why we have the 50% increase, that's a complicated issue, but transverse welds are usually more uniformly loaded. The testing of transverse welds shows that they do not fail along the theoretical 45-degree throat of a 90-degree T-joint. Rather, that angle rotates to a point where it's much more perpendicular to the applied load. And that rotation of the throat results in about a 38% increase in the capacity of the fillet weld. Now, some of us talk about the quest for the 12%, and that is explaining where that last 12% came from. It's a fascinating story, frankly, and I have a theory. I'd like to see it researched sometime, but that topic needs to wait for another day. It just can't do it in this short time.
Okay, thank you, Dwayne. I think we have time for one more question. The question is, what is the suitability for a PJP all-around weld at an HSS butt joint subject to shear and bending?
Okay. Well, first, AISC Chapter AISC 360, the seal spec, Chapter J has a variety of cartoons with formulas to calculate stresses around the perimeter of tubular connections. And it's reflecting the fact that we don't have the same stiffness on all elements of the tubes. Now, if I understand the question correctly, it is a splice subject to tension and bending. And a PJP groove weld would be fine for that application. You look at the limit states on the throat of the weld, 30% of the electroclassification tensile strength, multiply that by the length, and if that weld is adequate to resist the applied loads, that would just be fine. Now, I think what's buried behind the question is the unfused root of those tubular joints. And here's the key issue. The weld will never be subject to bending about its longitudinal axis because we have welds on, let's assume it's a box for just a moment, and we have welds all the way around the perimeter. And so the root region is protected under those conditions. There should be no problem with the PJP groove weld of the right size for that application, and I'm assuming we're dealing with statically loaded connections in this question.
All right. Thank you very much for your responses, Dwayne. Unfortunately, that's all the